Look at a traditional incandescent light bulb. It produces light, but it is incredibly inefficient. About 90% of the energy it consumes is exhausted entirely as heat. Producing that much heat requires an enormous, continuous supply of metabolic calories. Down in the deep ocean, where food is scarce and temperatures drop near freezing, generating excess heat is a metabolic cost living organisms simply cannot afford. To survive in the abyss, these animals execute a method of light generation that completely eliminates waste heat. They do this through bioluminescence, the production and emission of light by a living organism. On the left, a standard light bulb radiates massive thermal energy. On the right, a deep-sea shrimp emits a pure, bright glow with zero heat signature. Because there is no thermal loss, this cold light achieves an energy-to-light conversion rate approaching 95%. Maintaining that level of efficiency requires an active, highly refined internal chemical reactor. Zooming past the organic tissue and down to the microscopic level reveals a biomechanical factory working with absolute precision. The process begins with a specific chemical fuel called Luciferin. That fuel bonds with a catalytic enzyme known as Luciferase. This enzyme acts as the physical engine block where the reaction will take place. When an oxygen molecule enters this system, it forces a rapid chemical reaction, breaking bonds and instantly ejecting a sharp spark of light. This strict physical interaction of chemicals constitutes a precise manufacturing process, allowing the animal to generate light exactly when it is needed. That single ejected spark is a photon, a discrete particle of light energy. By regulating the concentration of internal chemicals and controlling the flow of oxygen to its cells, the animal determines exactly how many photons it produces. It operates like a high-end LED array. The organism can maintain a steady glow or flood the system with oxygen for a blinding strobe effect. Managing the output of this chemical engine allows the animal to weaponize its photon supply for tactical use in the field. In the open ocean, light is rarely used for navigation. It's deployed as a survival tool. The manufactured light routes into specialized exterior organs called photophores, which cover the animal's exterior. These arrays execute a defensive tactic known as counter-illumination. From a predator's upward perspective, a midwater animal casts a dark silhouette against the faint surface sunlight. To execute the illusion, the prey matches the exact brightness of that surface light using its downward-facing photophores. It effectively deletes its own silhouette. The physical body remains entirely present, but the optical illusion renders the animal invisible to threats lurking below. If that primary camouflage fails and an attack occurs, the organism initiates a secondary tactic called the burglar alarm protocol. In defense, the animal instantly floods its photophores, erupting into a violent, rapid strobe of piercing cyan light. This flashing serves as a beacon. It intentionally exposes the attacker's location to attract much larger secondary predators to come in and consume the threat. From the microscopic chemical engine to the exterior photophore arrays, this biological network achieves incredible energy conservation and optical engineering. By eliminating exhaust heat entirely, nature has designed a lighting system that outperforms human optical engineering in both thermodynamic efficiency and tactical survival.